So I will discuss mainly the binary sources because it's the main interest for the current gravitational wave detectors, LIGO, Virgo, and all the other nodes that are joining now. There are those types of sources like well, cosmic backgrounds and other kind of sources which I will not talk about. So for slowly, let's consider the simplest case of a slowly moving source, which is weakly self-gravitating. So the velocities inside of the system are small, and the Schwarzschild radius of the source in terms of the size of the source is also a small parameter. So the Schwarzschild radius is the total mass of the system times 2 times g over c squared. So a typical example is a binary system in the early inspiral phase. So the distance d is the distance between the two compact objects, and the Schwarzschild radius is the one of the total mass. So, but if you have one mass much bigger than the other, it's mostly Schwarzschild radius of the largest mass. So binaries admit actually only one small parameter, because here you can think that there are two small parameters that are independent of each other, but they're related. So if you define the reduced mass by this equation, the total mass I defined it earlier, where the gravitational binding gives you an equality between the kinetic energy of the reduced one-body system and the potential energy of the reduced one-body system. So this is a Newtonian theory of gravitation. So if I can remove the mu here, and I have an expression between the total, the Schwarzschild radii of the total mass and the velocity over c. So you see there is a square relationship between the two. So corrections in V over c use corrections in the gravitational effects, so actually in G, if you expand in G. First order is Minkowski, and then you have first order perturbation G, and here you have Newtonian theory, and then you have V over C corrections. Another length scale of importance is the gravitational wavelength. So if you have a typical frequency of motion inside of the source, which is omega s, and d is the source size, then the typical velocities are well, the frequency times the typical length of the system. And something that we will derive later on, but I ask you to trust me now, is that the frequency of the gravitational wave is roughly 2 times the frequency of the source. So if you admit that, then the reduced wavelength of the gravitational waves, which is c over the frequency of the gravitational waves, is roughly c over omega s by this relationship, which is by this relationship c over vd. So for a non-relativistic system where v is less than c, we also have that d is way less than the reduced wavelength of the gravitational waves. So gravitational waves are much bigger than the typical size of your system. So if we put these length scales in a plot, we reach this diagram. So here is my system, my binary system, with the Schwarzschild radius here, which is very small length scale. The size of the system is d. And then we have the scale for the gravitational waves, lambda bar. So in the we can define the near zone, where r is less than lambda bar, where there is no gravitational wave, where this is the place where there is a source generation, the generation of them, and it's described by a post-Newtonian expansion. Away from the system, we solve the vacuum Einstein's equations. So it's called the vacuum zone, or the exterior zone to the system, so r larger than d. And in this zone, we can do an expansion in G, in the Newton constant parameter. When you have radius larger than the reduced wavelength of gravitational waves, then you are in radiation zone. and there you can perform a radiative expansion. So it's useful for computing the gravitational waves patterns to do a multipolar decomposition, to decompose in multiples over in this region. Now, this near zone and exterior zone have a common region because d is less than the reduced wavelength. So there's a match between this kind of series and that kind of series. So the way that the formalism, post-Newtonian, post-Minkowskian formalism works is that there is a match expansion between the post-Newtonian expansion in near zone and the post-Minkowskian expansion in the exterior zone. So because there is also a change of energy between the two zones, the fact that there are gravitational waves exiting the system, it means that this system has radiation reaction. So it's, by conservation of energy, the energy that radiates out of your system has to be taken from your system. So in this zone, you have a post-Newtonian expansion with the boundary conditions given by some multipolar radiation reaction due to the radiation emission. So this formalism is the main formalism used for deriving gravitational waves. And here I'm not going to discuss all the formalism, of course, but just a very subset of it. So just to show you a picture, well, a video here. So if you have your system, you see that the typical wavelength of gravitational wave is way bigger than your system. And here, where the matching region is very small between the post-Newtonian here and the multipolar P-n expansion. Of course, when you are close to merger, all this breaks down. It's only for the inspiral phase that it is valid. So in this lecture, we will derive the motion at the lowest order. So in the near zone, we will use Newtonian with the radiation reaction, which is actually, we will see a 2.5 P-n effect, post-Newtonian effect. I will explain that later on. And the exterior zone, it will be just Minkowski with linear gravitational waves, which means it's post-Minkowskian at first order, 1 P-n. Do you have questions already? Before I move on to now explain. Don't hesitate to interrupt me for questions. Okay, so let's look at weak sources, in the sense that we can use linear perturbation theory. And at this point, I'm not going to restrict the velocity. We're going to do that later on. So we saw last time in the first lecture that the key equation in linearized theory, once you impose the harmonic gauge or the Donde gauge in terms of the trace reverse perturbation, which is h bar, and if you have a matter stress tensor, which is conserved in Minkowski, the equation that governs linear perturbation is given by this one. It's a wave equation sourced by the stress tensor. So we can solve this equation. This is similar to electromagnetism. There is a green function which solves the harmonic the Lambertian in 4 dimensions, equals to a delta function. So it exists and explicitly is given by this well-known formula, where you have a delta function in terms of retarded time. So the retarded time is t minus the spatial distance between x and x prime divided by c. And the x0 is always times c times the retarded time, so that you have a length. And x prime is the same with primes everywhere, with a prime on t. So with this green function, the general solution of this system is given by this, where you have to be careful with boundary conditions. Here, this green function is the one appropriate for the retarded system, where there's no incoming wave coming from past null infinity. So fields are outgoing only. Now recall that outside the source, we can use the TT gauge. And this CT gauge is given by a projector acting on the harmonic H. And we worked out the property of this projector last time. So if we are outside the source, the TT gauge perturbation, which is the one that contains the gravitational wave radiation, is given explicitly by this formula. We use a projector and we apply it on the solution of the linear equation. So here, we had the green function as just substituted. So it's 1 over this distance, and there is a delta here of the retarded time with an integral over x prime. So you can resolve that delta and replace explicitly a time that appears only in the stress tensor by the retarded time, so that you're left only with the integral over x prime that appears at 3 places: in front here, inside of the retarded time, and in explicitly for t. So that's what we need to solve. So note that this metric perturbation depends upon the integral of the spatial components of t. And you might be might worry why the energy of the matter does not matter here, does not appear. In fact, the temporal components are related by the stress energy conservation. So indirectly, they matter. So to do that computation, we are going to expand x minus x prime. So imagine the source as a typical distance d, and we integrate over the entire source. But the detector, which is this distance x, is very far away. So we can, so this distance x minus x prime, so x is the location of the detector, x prime is a point inside of your source. This distance is nearly the radius of the center of mass of the source to the detector. So it's nearly r, and there is a small deviation. And if you do a bit of trigonometry, you have to project x prime on the unit x to find this distance here. X prime dot x is actually this distance. So it's r minus this quantity plus suppressed corrections, which are order d squared over r. And since we are looking at the large radius limits here, and this is real astrophysically, we're talking about hundreds of megaparsecs, so it's really suppressed, this number. So we can approximate it with this. So now I replace my at the leading order here, there was a 1 over x, so I can say it's 1 over r. The next correction is very suppressed. And here inside the integral, I need to keep some dependence in x prime because that matters. I cannot just substitute r here, but I have to keep the first order one. All right, so the result is that the gravitational waves have a dependence as 1 over the distance. So they decay as 1 over the distance, not 1 over the distance squared. So it's like electromagnetism when you have radiation, a radiation field that is retarded with respect to a source. It's also 1 over distance. Okay, so now we are reduced to this much simpler equation. Let's now take the assumption that there are low velocities. So to study low velocities, it's better to do a Fourier transform, and it will be clearer. So I want to do a Fourier transform of this stress energy tensor. So it gives you an integral over k of some Fourier coefficients, and with these Fourier modes, right? So now we take the assumption that V is less than C, and we know that it implies that lambda bar is much bigger than D, that we derived earlier. So now, what does it mean to have low velocity in terms of these Fourier coefficients? Well, in terms of the Fourier coefficient, there is a special typical source frequency here. If I plot the amplitude of these coefficients in terms of omega, there are various, well, each coefficient will have a different function, but they're all cut off around the source, around omega s, because that's the around the maximal frequency of the source. So this is one property of these Fourier coefficients, that are cut off after around the frequency of the source. And moreover, in terms of the original non-Fourier transform, of the original special stress energy tensor, is non-zero only inside of the source, when x prime is less than d. It's obviously zero outside the source. So when we see this number, that's the one, that number is the one that is important. This is the one that appears in here. I will appear after the Fourier transformation. So here actually, omega times this number. So this one is less than omega, the source, because omega is cut off by omega s. This quantity is cut off by d. And therefore, since omega d is less than c, which is part of the assumption, this is less than 1. So it means that in this Fourier decomposition, this exponential is very quickly oscillating. There was this number very small. So we can expand. So I will take the first term and then expand this term, which is a small number. So I can make an expansion like this one. Making this expansion in the Fourier domain, if you do the inverse Fourier transform, you can see the analog in the spatial domain. And what it means is that you do an expansion in time derivatives. So if you look at this number, you see that the omega comes from the Fourier transform of the time derivative here. And this is the leading term without the dependence in x prime inside of the argument, or the first argument. And that's one, this is just a number if you do the Fourier transform on time only. So you see that you get an overall coefficient if you just inverse Fourier transform on t, and you get just a dt. Okay, so that's what's happening, what you can do because of the low velocity. You can do this expansion. So naturally, what appears here will be the multiples of the stress tensor. So you have the stress tensor, and here you have the stress tensor with the derivative times x here. So it's natural to define the multiples by these integrals. So the first multiple is just the integral of the stress tensor over the entire source. And then the other multiples is when you multiply with, we have an extra x here, and you integrate over x, only the source, etc. So you have an infinite number of them. So if you use these definitions of the multiples of the stress tensor, you get all in all. So I will just, this is the overall coefficient that appeared earlier here. There's the overall coefficient. And now we want to perform the integral d3x of t. And now I replace my t with my expansion, and I perform the integral. So, and perform an integral, I will use this definition of the multiples. So the first term is just the multiple itself, the lowest multiple, coming from the integral of this term. So it's this term here. And then the next one, well, we have the x, this x that remains in front. And then this one is the x prime m, over which to integrate, that appears inside of this definition of the s. Right, because there is the x prime here inside and the x prime here. So this is this multiple, and there is a time derivative. So there is a dot here, meaning the time derivative of the second multiple, etc. So at high orders, you get two derivatives, and you get the higher multiple and two x's. Okay, and all this is evaluated at retarded time. Because the leading order here, you see, is evaluated at retarded time. They're all evaluated at retarded time. So retarded time t minus r over c. So this is why there is this retarded here. Okay, so that's the result. So note that this term contains a time derivative and there was an extra scale. There was a power of c, and there was extra dimension here because of this x. So the overall scale is omega s d over c or v over c. So it's a suppressed v over c correction in respect to this one. So the leading term is this one, and you have v over c corrections, v squared over c, etc. squared. So the conclusion is that weak sources with low velocity emit gravitational radiation that is essentially determined by the lowest multiple moments. This is why the multiple expansion is very useful. So we don't need to know all the structure of the source. We only need to know its lowest multiple moments. So remember that the gravitational wave power is a square of h. So you will have to take derivatives and take a square. So this one we will see later on, that is a 2.5 post-Newtonian effect. And I did not prove that yet, but you can already see that here you have a v over c subleading term. So in the post-Newtonian formalism, you count by square powers of v over c. So this is a half post-Newtonian correction. But since there is no mixing of these two terms when you do a square, when you have to do some representation theory that I don't have time to explain, it will be only this one squared. So it will be actually a v squared correction. So a 1 pn correction with respect to the leading term. So it will be a 3.5 pn correction in total. But I first have to prove a bit all this, just to put some some orders and to see where are the orders of the corrections here. So these multiples are not very intuitive. We have much more intuition for the multiples that are these ones, where you integrate the 0,0 component, which is the mass, or you integrate T00 multiplied by xi over all x, and that one is the mass monopole, or the mass dipole, sorry, the mass dipole. This is the mass monopole, or the mass. This is the mass dipole. So there are also momentum multiples, which is given by the 0i components, and with higher momentum multiples. So to understand better, we need to relate the multiples of Tij to these multiples. And in fact, these multiples are related using the conservation of the stress tensor. So now let's do an exercise because I've been talking too much. So obtain the time derivative of the lowest mass and momentum multiples. So here is a convenient notation for denoting all the multiples. L is any set of indices, which is a symmetrized set of indices. So it can be a single index I, or no index at all, or ij. So same for here. So all these are the mass and momentum multiples. And so using the conservation of the source energy tensor, try to obtain these relationships, these time derivatives. The S's, I remind you, are defined here. The S's are the integral of the special component of the stress energy tensor. So keep that one in mind. It's a very simple relationship. With the index k on the right here, it means that there is an xk here. I should have also copy-pasted that here for the exercise, but I forgot. So so try to work these relationships. And also ask me questions if you need to. All right. So do you need more time, or you think we should correct? Anybody wants to speak out?
It's okay either way, I think.
It's okay either way. Someone has strong feelings for correcting or not correcting?
I think it's fine to correct.
Okay, let's go for it. So, so it's pretty straightforward, but it's good to be convinced of these relations. So the time derivative of the mass multiple, so it's the time derivative of the integral of d3x of t0, 0. So you can enter this time derivative inside of the integral. And now you use the stress tensor conservation, the zero component of it. So it's minus the I sum here. And now you can do integration by parts. And since the stress tensor has just a finite extent at special infinity 0, so you just put it to 0 for any volume larger than the source. So the mass is conserved. And you can be a bit surprised why the mass is conserved, because you're emitting gravitational waves. But in linear theory, there's no back reaction of gravitational waves. The mass of matter is conserved. You have to go to second order beyond the linear theory to start to see that the mass is not conserved. So in linear theory, the mass is conserved of the matter. Now the dipole changes with t in the following way. So you act with the time derivatives, it passes through. Xi is just special, so you pass through. You use the conservation, so it's minus the j here. You integrate by parts, so now the surface term, I just put it to 0 because it's 0 far from the source. So I just have plus dj acting on x here with a d3. So that gives you c times the momentum monopole. For the third one, so you apply d0 here on the mass quadruple. So it's t00 times xi xj. You use the conservation, so you get this one. You integrate by parts. So you have two different terms. So I just symmetrize with a factor of 2, and so I give you a delta, and so you find just the p ij and the pji here. So the others is the same kind of. There's nothing conceptually new. So you have the conservation of momentum, which you can obtain easily. And here, this is symmetric. So if you take the anti-symmetrized part of the left-hand side is 0. This is actually a conservation of angular momentum that you can see here. And this third relation we will need later on. Okay, so now we are convinced that this is true. We can combine these identities to express the spatial multiples of the stress tensor in terms of the mass and momentum multiple moments. So I will need these two relationships, and you see now that Sij, if you do a second time derivative here, you have this one. So there's a symmetrization, which I didn't put here. Yeah, because the antisymmetric part is 0 by conservation of the angular momentum. So this is automatically, the time derivative is automatically symmetric. So this is true. So now let's go back to our expression. So this is our expression. And now the leading term was this s. And now we can replace the s with 1/2 second time derivative of the mass quadrupole. And then we get this factor. So that's the statement that the acceleration, which is these two time derivatives, so it's an acceleration, the acceleration of the mass quadrupole sources gravitational waves. And this is a statement at leading order in the expansion V over C. And I recall you that this is the form of the projector. So that's the final result for the linear order gravitational waves in terms of the mass quadrupole. Let's compute now the radiated energy. I copy-pasted the formula that we just derived here. And this is the formula for the radiated energy that we derived yesterday. You can check that this is the right formula from the lecture. So you just substitute now this expression. So first the projectors. So a projector of a projector gives you zero. Well, give you the projector. Sorry. So there's only one projector in here. Now I'm missing a time derivative here. So there's a time here, and so there's these 3 time derivatives here. So here there should be a third dot. Otherwise, it doesn't make sense here. So you have this expression with the factors 1 over r that cancels out, and you have a factor of 8. So you can either put the mass quadrupole, or you can put the traceless part of the mass quadrupole, because anyway, there is a projector that will remove the trace as we saw last time. So you find a formula like this with an extra time derivative. So the angular integral can be done. So if this is the radiated energy per unit sphere, but you can perform that integral, and we are going to do it explicitly. And you get this. So now you find the radiated for the total power, which is this Einstein quadrupole formula. So I told you that there was conservation of energy was very important here, because there was a radiation reaction to the source due to the emission of gravitational waves. So let's look at that. So we have a conservation of energy. So the energy of the source is minus the energy radiated. So for a binary source, the total energy, so it's the kinetic energy and the potential energy. So you can do the effective one-body reduction by calling the reduced mass and the total mass that we did before. So M1 times M2 is actually exactly the same as M mu, right? Just from this relationship. And the sum of these 2 kinetic energies, you can just rewrite it as the kinetic energy of the center of mass and the kinetic energy of the reduced system, where R is the relative distance between the 2 bodies. So now, by the Kepler law, this velocity is just dm divided by r. So these 2 terms combine into a minus 1/2. So if you are in center of mass frame, this term is just 0, and this is the real energy. Yeah? And this is the energy of the system. So the derivative of the energy of the system with respect to the source is just given by this expression. Now we have to equate this with the power. And so just in terms of the coefficient, the variation of the radius is given here by a power g over c5. So this is why, so 5 means 2.5 post-Newtonian. So this is why the gravitational wave emission brings as first contribution a 2.5 plane correction to the motion. So this is what I was explaining here, this multipolar radiation reaction here, coming from the gravitational wave emission in the radiation zone that backreacts on the source. So there is an entire formalism here, and here is just a sample, just to give you an idea. So the motion, the Newtonian motion, and these different types of corrections, and these corrections are first conservative in the sense that they're described by Hamiltonian, and they do not induce gravitational wave. They're just relativistic corrections due to the relativistic fields and due to gravitational field generated by these bodies. So, and this is what explains, you know, the precession of Mercury and these kind of observables or deviation, different deviations from Newtonian theory. And this radiation reaction that I just derived here is this 2.5 pm term here. This next radiation reaction term, as I explained to you, is this 3.5 pm here. There are many other terms due only to the conservative motion that is changed. And there's an entire formalism for that. That involves the Fokker, Lagrangian, ADM Hamiltonian, and various other methods. So I don't have any time to cover this, but here are some references. So the current state of the art is 4 pm, for post-Newtonian order. And there are already some terms known at higher orders. So to conclude this section, let's do this exercise.
Sorry, Geoffrey.
Yes.
Can you go back to the previous slide where you talk about radiation? Yes, here. Yes. So you call this the E's 0 pn, while we clearly see V squared or G over R. So.
Well, this is the Newtonian. This is the Newtonian expression. This is the Newtonian expression.
I agree. This is the Newtonian expression,
so
but
European.
But I mean, okay, it's just a name. I mean, it's not.
It's just a name. It's just a name. It just means that this is the leading order Newtonian result. So you have corrections of V over C on that. Yes. Yeah. Are there other questions? Okay. So I propose you to look at this exercise because that formula is a bit mysterious. You see it like this. So by the way, I thank Ali for this formula. So I guess it was done by Thorne or by other people before, but it's a very useful type formula. So let's try to prove this one first. And then allowing to prove this one will allow to prove this one, and then finally arrive to this one. So of course, if you just plug, I mean, these explicit values in Mathematica, you do the integral of the sphere, it should match, but this is not obvious to derive it from Mathematica. So here is the way to analytically derive it. And to also understand more generally the integral of various powers of n that appear. So do you want more time or you prefer to have the solution?
A little more, please.
Need more time, huh?
which will continue, I think.
Yeah. Okay, very good. So, so the first one, the easiest way to do is to use SO3 symmetry. So the expression is explicitly SO3 invariant on the, because there is vectors. Two vectors can give you a scalar and the SO3. So we can just assume that K points in the Z direction and then use SO3 symmetry to restore the indices. So let's just assume it's Z in Z direction, we have just a cos, because n here is just a cos theta. So now you can perform the phi integral, it's a 2 pi, and d theta, it's better to work with cos theta as an integration variable, and then you see just an exponential. So, and that one goes from -1 to 1, because you go from 0 to pi for the theta. And then you get these two exponentials that combine into a sine. Okay, and then you restore now you have to find a scalar which gives you back kz, and there's only one possibility, is the norm of k. Okay. So this one is trivial because you just apply derivatives on the left hand side. So you replace sine over k by its left hand side, and then you apply derivatives, and you find each time factors of minus I n. So the factors n just show up here. I'm a bit confused with the minus now.
It needs to be put in the denominator, so it should be 1 over minus I to the L.
Yeah. Yeah, because that's right. The I here cancels the minus I that comes, and then it just cancels out. Then it's right. And then for this integral now, so now the way to do this is to look at the Taylor series of this expression. So the Taylor series of sine x is actually x to the power 2 n, where n goes from 0 to infinity. When you divide, when the first term is really there's a k plus 1, but then if you divide by k, this is a leading order term. So you need to know this Taylor series, and you plug it in here, and now you have you take k derivative and you put everything to 0. It means that the L here has to be equal to 2L, otherwise you get 0. Otherwise, you either, if you are n lower, all the derivatives are just killing all your terms, and if your n is higher, then you are left with some k that you put that to 0 at the end. So it's only 2n equals L that remains. So so then I to the power L is I to the power 2n. So it's minus n to the power n, right? Right, so and then when you take all these derivatives, you will get a L factorial that will come because you act on k to the power L, and this is the same as 1 over 2n plus 1. So overall, this factor minus 1 cancels out here, and you get this factor in front, which is L plus 1, and you totally symmetrize all the indices. So that one, well, the easiest way is just to compute now explicitly without any indices. So you find just L equals 0, so you find 4 pi. That's the norm of the sphere. With two ni indices, so that's to be a pair number, otherwise you get 0 here. So if you're this pair number, L is 2, and you have it on the delta. And you have 4. So L is 4 here, so you have a factor of 5. And now we have to be careful with the total symmetrization here. The way to think about it is that you have 4 indices, so you have 4 factorial ways, but then each pair you have a factor of 2. And you have also a factor of 2 because you can exchange one pair with another pair. So in total, you have 3 different types of terms. So these are the 3 different types of terms. And this is weighted with average 1. So to see if you have 3 terms, you have to put a factor of 1 over 3. So 5 times 1 over 3 is 15. And now if you just use this relationship into the definition of lambda, then you get this. So I will break now for 5 minutes to have a short break. And then I will continue with the next section. Don't hesitate to ask me questions. I will set at 3:10. All right. We start now. So now we have all the tools we need for addressing the quasi-circular and spiral of compact binaries. So this is the application of this formalism. So let's do the computation now. We neglect all these conservative PN corrections, but we'll keep the Keplerian motion plus the radiation reaction. So this 2.5 PN radiation reaction due to the leading order gravitational wave emission in the exterior zone. So Keplerian motion in general is gives rise for bond orbits to elliptic orbits. It's a bit more complicated. I will look only at quasi-circular orbits. So again, the Kepler law gives you the relationship between the frequency of the motion and the gravitational potential. So you can write it this way: omega s, so the source frequency squared equals g total mass divided by r to the power 3. And the law of motion is given by the Freix balance law of energy, where I derived this equation for the source, and the flux of energy, where I corrected the typo with the third derivative of the mass quadrupole. So the only thing that we really miss here is a quadrupole from a mass in circular orbit. So to start, so let's try to derive it by starting from the relativistic expression of the stress energy tensor of a point particle, so which is given by this. So we have two particles, and given by the stress tensor is the mass times the velocity, times the velocity with index mu and nu with a delta function. So in the lowest Newtonian order, the stress energy tensor 0,0 component is just mc squared times the 3 delta. So it's pretty easy to see, but just deduce that. And then the quadrupole formula, well, we need to compute this second moment of the energy of the stress energy tensor 0,0 component. So it's compute that is given by this. So STF means symmetric trace-free component. So it basically removes this trace. But we don't strictly need that, because in the quadrupole we can just use the moment itself. X0 here is the relative distance between the two bodies. So the position of the first body minus the location of the second body. So you need to obtain this one. So you'll think about it for a couple of minutes.
And
yes,
sorry, what's the R0 in the trace term?
Is the norm of x0i.
Okay.
Yeah, so this is really the trace of this
term.
So you take the trace, and minus 1/3 the trace times delta. So that gives you the trace-free part. The symmetric part this is already symmetric by construction, because there's an I and j here. So you can ignore this and ignore this trace. We just really need the moment without the trace-free part.
Thanks.
Can I ask a question?
Yes.
When we neglect this conservative correction, but some of them come down to 1 and 2 pn.
Yes.
But are there like larger correction than what we compute, or how can we know that there?
So yes. So with respect to the motion, the dynamical motion of the bodies, it's a larger effect, but these effects do not generate any gravitational waves, because they're conservative effects. So the leading order effect in the gravitational waves is caused by this radiation reaction on the Newtonian, on the 0th order Newtonian trajectory.
Okay.
So this conservative change should induce corrections which are subleading in the wave zone.
Okay, thank you.
All right, I think that you are nearly there, no? Or do you one more time? Okay, I think we should move forward. Let me give you a solution. So this is the expression for stress energy, the relativistic expression. So for relativistic motion, the proper time is defined from the line element minus the line element. We are here in Minkowski. So there is an overall factor of C, and the special components, I can replace them with the velocities times dt. So dx, I put an overall dt on numerator and denominator. So I get this expression. So this is the standard Lorentz factor minus 2 in front. So the relationship between the proper time and the coordinate time in Minkowski is given by the Lorentz factor. So here's the expression, the relativistic expression. When we can integrate over the time because we have this delta function here. Now we replace d tau by dt, and we have a delta t. So we just replace it. And the overall factors, so it's a gamma because there are 1 d tau here and 2 d tau at the numerator, at the denominator. So this is an inverse relation, so we have a gamma at the numerator. So the zero component is given just by this. So Newton animates this gamma factor goes to 1. But this is the full expression. So now we need to do that integral. So the mass multiple is given by these two sums. So the delta 3 with the integral gives you just the sum of the two individual terms with the explicit values of x1, x2. And we can rewrite this in terms of the center of mass and this reduced radius, the difference of x and x2. And the center of mass motion, we're assuming to be, we assume that we are in a frame where the center of mass motion is just 0. So in the center of mass, this is the correct expression. Okay. So now so if we have a circular motion, this relative coordinates xi, I spell it into Cartesian coordinates, x0, y0, and z0. I will assume that the motion is inside the z plane, z equals 0 plane, with an x and y coordinates. So since the motion is circular, it's given by the distance, the radius, times the coefficient since. So I normalize my cos and sine by adding a phase just for convenience. So it's just a shift of time. So the mass multiple, mass quadruple, given by this expression. So so the 1,1 component is the square of x, given by this one, times mu. The 1,2 is the product of x0 and y0. And the 2,2 is the square of y0 times mu. The other components are 0. So now that we computed m, we can compute the metric. perturbation. So here we are looking at the polarization tensor with an arbitrary direction, and that's this theta and phi, the interpolation of BT being the point in the sky where we are looking at. So this is the angular coordinates where the binary system is located in the sky. So with respect to the observer. So so now we have to make that multiplication, and I don't want to spend any time on this. This is just some trigonometric functions, so you can work it out. You just plug it the definition of the projection tensor as a definition of the normal. So it's a bunch of trigonometric function times the m, and if you compute, so there are two polarizations here. If you compute polarization in terms of these quantities, you find this result. So now I plug in the explicit values for these m's. So you see that they depend on the fixed radius r, the frequency omega s, and I need to do 2 time derivatives. So it will introduce me some omega s squared. And now it will depend both on theta and psi and on t. So there are various trigonometric functions here, and you have to work out the math. And if you do it, and this is a bit too long to do in this lecture, but you can just plug it in and check. In fact, what you find is that the theta just factors out, and the phi and theta and t just combine into a single cosine. And here they combine also into a single sine. So that's the magic of the computation here. It's not totally obvious from these expressions, but it works out. So they just recombine nicely. So this t again, this t here, and this phi here, just recombine nicely. And the overall factors of theta, you see the dependence in theta is different between the plus polarization and the cross polarization. You have a factor of 1 plus cos squared theta over 2, and for the cross polarization, cos theta. You have this factor of omega s squared because of the 2 time derivative, r squared because it's a quadratic in the mass multiple, and it's proportional to a overall factor, so mu as well. The 1 over distance, that was part of the definition of h here, and the overall factor g over c4. Okay. So here is finally the claim, the proof of the claim that the quadrupole radiation is twice the frequency of the source, simply because what you find here is 2 times the frequency of the source. So in this, the quadrupole order is actually exact. If you include higher quadruples, you might have some mixing. So this is not an exact relation in general, but for the quadrupole, it's actually exact. Here you have retarded time because it's the definition. Huh? You have to evaluate the quadrupole at retarded time. Right. So you find an helicoidal structure, which is actually natural, because when you have circular motion, so in space-time, you're doing a wall line, which is an elliptic, how do you say in English, an ellipse? Where you have an helicoidal structure. So if you shift time, you should be able to shift phi, because when you shift time, actually you are a bit further in your cycle. So you actually shift you make a rotation, and you are back with your same system. So this is why actually the t and phi recombine nicely, because of this helicoidal structure. So I said that already. The angle is the angle between the normal to the orbit and the line of sight. Yeah. So it's the view of the, so theta is really that, the normal to the orbit and the line of sight, and the distance r is a constant. So now to interpret theta more physically, here is a view generated by this S collaboration, where you have a fake background behind 2 black holes colliding, which is actually the Milky Way. This is just for fun. And you see the 2 black holes colliding. to explain the feature of that the picture is a bit too much for this lecture. Where you have the black, you have the Einstein ring here, the light ring. But the main feature here is that for theta equals 0 means you see the plane, the plane where the motion occurs is orthogonal to the line of sight. Edge on means that the plane of motion well cuts your line of sight. Is this one. Actually, inside of the light ring, you have an entire picture of the universe. You have 2 times the picture of the universe here, or an infinite number of times actually, if you are close to the light ring. But anyway, it's a different topic. So if we compute now the angular distribution of radiated power in the quadrupole approximation, so this is the formula that was derived earlier, and this is the formula we just derived for the shape of the gravitational radiation. So now we want to plug that in, and note that we will square this, so we have a cos squared here, and the average of a cos squared is 1/2. You simply take the trigonometric formula. So cos squared is 1/2 plus a cos, minus a cos 2 times the frequency. And so if you average over the frequencies, the cos has an average 0, but the 1/2 remains. So when you do this average, all this cos and this sine will average to 1/2, both of them. And you will have a difference because the only difference between these 2 terms is the theta term. Here you have this factor squared here, and on that side you have this factor squared. And they will sum up for the total energy. So overall, you have the global factor and this function of theta, which is the square of these 2 functions. So if you see that function, and I plot it here, sum of theta, so its amplitude grows if you go, so here's a small amplitude for g theta for edge-on systems, and if you have a face-on system, the amplitude is bigger. The overall integral of theta is 4/5, turns out. So the total power radiated, if you do integral of theta, is given by this formula. And you can rewrite in terms of the source frequency, in terms of the velocity, is given by this. Okay, so that's just for information. That's and it's a huge amount of power. You have to compare that to standard powers, astrophysical powers. Yes, there's a question?
Yes, so if you're in the edge-on direction, we don't see the cross polarization, right? Because there's
That's right.
cos theta.
Yes.
And then, I mean, for example, LIGO, because it measures the difference between the distances of these bodies, does it see the plus polarization, or is it only?
So you have well, so there are 3 detectors, and they can combine the 3 of them. They can detect from where it came from the sky. So that's one of the features of the fact that they are. So the fact that they are physically located in different places on the Earth matters, because then they see a different polarization arriving to them, slightly different. And then they can pinpoint the point of the sky where it came from.
Yeah, my question is that, I mean, consider just one LIGO site, right? It has 2 arms, perpendicular arms.
Yes.
And then if you only have assume that we only have the plus polarization, so it scales both arms with the same amount. So perhaps we don't see the effect of gravitational waves. Maybe I'm misunderstanding, but.
So what they measure with one single detector is a combination of the polarizations. So which depends on the source and the orientation with respect to the source. So one detector will always find a combination of the polarizations.
But according to this formula, if we are in the edge-on direction, there is no cross polarization.
Yes, there's no cross polarization. That's right. Yeah, you don't see it at all because of this indeed this cos theta. But well, in that case you see that polarization, so you detect that one only.
Yeah, but this scales both the arms with the same amount because. Maybe I can ask you later.
Yeah. I think now I see what you mean.
Okay. Yeah.
So you mean for the detector, the signal would be heavily suppressed.
Yes.
Yes. I think that's right. Yes. Mm. Yeah, and the signal then will be suppressed. No, you're right. Mm-hmm. Actually, it even happened for this event for the neutron star collision.
Uh-huh.
In that case, the Virgo didn't detect the event because it was in this spot indeed where it could see only the post-polarization. I think that's what happened. And then, but LIGO detected them. But the three combinations, the three observations were then since Virgo didn't detect it, meant that he was observing precisely that case, and so they had to pinpoint the angle in the sky.
Okay.
Yeah, that's right.
Okay, thank you.
So let's now derive the fact that there is inspiral motion, because so far I took that for granted. We can now derive it. So the emission of gravitational wave cost energy is taken from the system's total energy. So this is the formula that was derived earlier. So the energy of the source is varying in this way. And it's negative because it's equals to minus the energy that was radiated from gravitational wave, which is a positive. So it means that R is decreasing with time. So there's a shrinking of the radius, but the frequency of the source by Kepler's law is given by this. So it means that the frequency is increasing with time. And now from the formula of the radiated power, here, the power is proportional to omega s to the power 6. So if omega is increasing, the power radiated increases and increases very fast because of this power 6. So there's this runaway process leading to coalescence that is accelerating. So that's the proof that there is this inspiral. So the motion is quasi-circular, and this was the assumption that we use, as long as the radial velocity, the change of radial velocity is way less than the velocity of the inspiral, of the circular motion. So see now that this is equivalent to this relation in terms of frequencies, because we will have to check that later on. So I'll give you a minute to check that. Use this one. Huh? Okay, so I think we should not spend too much time on this, but so this is, you use a Kepler's law and you take the time derivative of it. So this case like omega s to the power minus 2/3. So it's minus 2/3 omega s divided by omega s dot divided by omega s times r. So if I put back 1 power of omega s, this is the velocity. Now, if Rs is less than velocity, the same as this frequency of the source over omega squared is less than 1. Since they are commensurate, it's the same as the frequency, the frequencies of the gravitational waves with a factor of 2 pi that I can remove. So it's just this one. Okay, so that's the quasi-circularity hypothesis. So now we have obtained this gravitational waveform, and so far we used these parameters, the source frequency, the reduced mass, and the radius between the two objects. So now let's use this relationship, this Kepler law again, and let's replace the source in terms of the frequency of gravitational waves, and we introduce a new quantity, which is called the chirp mass. So the chirp mass is a very special combination of reduced mass and total mass, with powers, a bit mysterious powers of 3 to the power 5 and 2 to the power 5. Now, if you use these quantities, so now you keep only the frequency of the gravitational wave. So you remove all the omega s in this expression, and you remove all the r's, and you keep just the total mass, the chirp mass, and the frequency of the gravitational waves in this expression. Could you just do it for the first term to see what you get? It just takes a minute. So what you notice, what you're currently noticing, is that the mass cancels out. So there's only the chirp mass that's left in the frequency. So this is why the chirp mass is interesting. So you rewrite it and you find the chirp mass, some factor, the frequency. And that's it, there's no more parameter. All the dependency on the mass is through the chirp mass at this lowest Pn order. So this is why when you observe this inspiral, the first thing you can find is the chirp mass, because all the dependence in the masses is in this combination. So if you re-express in terms of the chirp mass, the power radiated, these are the formulas that you would find. It's just a substitution. So that was easy. So now prove that if you have, this is the energy. So that's the standard energy that you know from Newtonian theory. You can rewrite it in terms of the chirp mass, in terms of the frequency of gravitational waves. So that's another way to write down the Newtonian potential energy, which is adapted for gravitational waves. So it's just a substitution. So, and from this one, you can deduce the evolution of the gravitational wave frequency using this power radiated. And using the flux balance law, of course. You could just try it. Okay, so for this substitution, and you see that the powers of m just cancel, you find this one. So there's nothing really to prove. So that's checking. So to get the flux balance law, now you have to take a derivative of this with respect to the time. So now you imagine the frequency depends on time. The mass, stroke mass is still fixed. And you equate it to the power radiated. So, so now if you do it properly, you should find this expression. So this is a differential equation, ordinary differential equation for the frequency of gravitational waves. So it's possible to just integrate it. So we have a power 11/3, so we get a power here 3/8 for the frequency. Minus 3/8. So now what you observe from this frequency is that there's an integration constant, which can be interpreted as the time of coalescence. So this function, if you plot it, is something like this. It goes infinity at a finite time. So that's the coalescence time, according to this assumption, to this approximation. And the quasi-circularity hypothesis, if you just plug now the solution here, you get this equation. So this has to be less than 1. So this is a cutoff on the frequency. So there is a specific value of the frequency which you stop to be quasi-circular. And you start a transition. Okay, so so now to have the proper waveform, we have to be consistent. So here we derived the motion, assuming that we have a Newtonian motion plus some variation of your constants. So now let's try to do it consistently. So we start with the inspiral. Well, now we start, instead of the circular motion, we start with an inspiral, where we have to now replace these parameters with the one that are evolving in time. So the radius now is evolving in time, and the frequency here is also evolving in time. So the frequency now is really a tail integral of the history of the frequency of the gravitational wave or the source. So the prescription here to have a self-consistent description is now to look at this motion where the radius is the one that's evolving in time, that can be solved from this solution. You can also compute the radius evolving in time from Kepler's law. And there is a frequency, which is the integral of this frequency. So if you compute that integral, it's given by this. So, so in the formula we derive for the quadrupole, we have to take into account these changes now to be self-consistent. So the quadrupole moment was given by this formula. That's what we did before. So this is the quadrupole moment, the original ones. So now we replace R with the R that evolves with time, and we replace the frequency with the time evolving frequency. It's really the phi. So when I say frequency, I'm sorry, I should have said phi. So with the evolution of phi of the phase. So this is, so the frequency is just in front of t here, but this is the entire phase of the system. So we replace it with the entire phase, and the convention in the literature is to put a factor of 2, because the phase is the phase of the gravitational wave, while the source has a phase phi divided by 2. This is just a convention. We should replace it with the phase of the binary system, which is this integral. So it's the phase of the gravitational wave, which is observable, divided by 2. So now, when we apply time derivatives, so we compute the waveform, we have to apply 2 time derivatives, and r dot is negligible as long as the orbit is quasi-circular. So the main terms come from the phase. So now we just need to take into account the phase change. So the final waveform is the one we obtained, where instead of the source at fixed frequency, now we have the full phase here. So if I look back here, so that was a waveform that we found, assuming that we have a circular motion. And now we don't have circular motion with a quasi-circular inspiral. So this total phase, we have to replace it with a gravitational phase. So there is this factor of 2 here, which is, so it means that this is really the gravitational wave phase. Huh? So we replace this with phi, and the rest unchanged. So this is the waveform obtained from the quasi-circular inspiral, with explicit phi, with this explicit frequency. We can shift the time just because we shift the overall phase with the overall constant. So this retarded doesn't mean anything, I can just remove it. It's just a shift of time, so which amounts to a shift of the initial phase. So the best way to write it is to write in terms of function of time before coalescence, because that's the special phase, is the special, well, this is a special time, is the coalescence time. So it's the best way to just write the final waveform. So this function is very simple. So here I substituted this frequency. So this is power 2/3 in here. So you see that there is a power at the end 1/4 here in front. And phi contains a power 5/8. So you can just plot that. If you put that in Mathematica, you find this kind of waveform. So this is, of course, the most crude waveform you can build up. So it explodes first, and then it does not contain any corrections. But it's still useful to compare it with the observations. So here, what do you see in this comparison? Well, of course, there's not this infinite behavior. Instead, there is a transition here where the two bodies have finite size and are very close to each other, and this is the deep GR regime. And at the end, you have the quasi-normal mode ringing, the fact that you have one single black hole ringing back towards a curved black hole. So here we can only describe the beginning of the phase. So let's try to at least match things here. So here's actually the real photos from the paper, and this is their templates, the templates that we used. So this is the match with the actual templates that they used. So once you remove the noise and you match with the templates, this is the full observation. And if you want to understand this, is the frequency of the wave in respect to time. So you see this shift, the frequency goes higher and higher. And that's called the chirp of the gravitational wave, because the frequency is going higher. So it's like the chirp of a bird. Okay, so now that we have all the data, so let's try to make the comparison. So here are the values, and here are here is to help you the match. So we have a solar mass is Schwarzschild radius is 3 kilometers. If you have 1 parsec, it's 3.3 light years. 1 light year is this amount of meters. The chirp mass again is this. So the amplitude, the waveform has an amplitude and a phase. Here is the amplitude that I took from the formula here. This is this amplitude. I remove this theta dependence. It's just an overall factor of order 1. Let's just look at this overall amplitude. And then let's look at the frequency. So you can express now this in physical terms by using these values as reference values and checking what is the amplitude that you will get, what's the frequency you will get for this system. So we start to be running out of time. So I guess I will just give you the answer because it takes a bit of time to do that computation. So if you compute the chirp mass of this system, you find that it's 28 solar masses. And so its Schwarzschild radius is 42 kilometers because it's 20, it's 14 times 3. This is the radius divided by 2, right? So now this is the conversion of the megaparsecs. So if you take this expression now, you want to put the overall values that are these ones, and the time before coalescence is 0.2 seconds. This is the reference time. So I want to use a 0.2 seconds here, and you put all these values, and you get that number out. So you can cross-check it at home. So you get that number, and so the scaling is the one obtained from the equation. And this is just the normalized value for this system. You can do the same with the frequency. So I use again 0.0 seconds as a reference, this mass as the chirp mass reference, and all these factors are standard factors, and I find 34. This is in seconds, so this is in hertz, so 34 hertz. Okay, so now we have this evaluation. So you can compare now to the LIGO sensitivity curve. So the strain is really the amplitude divided by the square of the average frequency, and the average frequency here is 30. Well, it's 34, so you get an overall factor of 1. Basically, cancel this factor, so it's basically 10 minus 22. So you are in here, and the 32 hertz is here, and you get when you have the coalescence, you go to higher frequencies, and the amplitude grows, and then you have a coalescence, and the amplitude just decays. So you see that you are inside of the LIGO band with this estimation. There are many challenges here when you go to higher PN orders. I just want to mention one because I find it interesting. So if you start to introduce corrections in the exterior zone, it means that when gravitational waves are sent from the binary system, which is depicted here, you have this wall line of the binary system here, it emits radiation, and so that radiation back reacts and re-emits gravitational waves that go inwards. And so it enters the system. So in terms of the evolution of the system, it means that you have an evolution which is non-local, because depending on its past history, it will have influence on the future. So you have non-trivial equations here. They're not standard differential equations. You have these non-local in time equations. And the mathematics of them is not fully understood. And it's interesting that, so it appears at 4 post-Newtonian order, because the first back reaction appears at 1.5 PN order. And this is already 2.5 PN that you have this radiation reaction. So this one appears at 4 post-Newtonian order. So there start to be challenges for the near zone binary equation of motion at 4 post-Newtonian order. And last thing I would like to say is the limitation of this formalism. So it's a perturbation series around a Keplerian orbit. And there are actually important relativity effects that are not apparent in this formalism. And the main one is the fact that there is an innermost stable circular orbit. If you look at the full, relativistic problem. So you can roughly estimate when you have a binary system that the innermost stable circular orbit of the system will be given by the total mass of the system, where 6m is the Schwarzschild value for a single black hole. But here you put the total mass, just as estimates of where the ISCO is. And so beyond that ISCO, there's no circular orbit that exists at all. So it breaks down, the initial perturbation theory breaks down because you start from a Keplerian orbit, which is quasi-circular, and it does not exist. So this regime is called a transition to merger, and so it's not covered by the PN post-Minkowskian formalism. And you can estimate the frequency where this formalism is valid to be the frequency where we reach that estimated ISCO. So this frequency of the gravitational we saw is 2 times the frequency of the source. And the frequency of the source we're using the Keplerian relation again is this. So now if you replace it with this estimation of the ISCO orbit, you get this one. And so if you scale with the total mass, which is the total mass of our system here, you get at 34 Hertz. So it's funny that this 34 Hertz is exactly the same as the 34 Hertz here. So actually this approximation, within this approximation scheme, we actually cannot say anything. We need to go to higher orders because this approximation scheme already breaks down at the place where it starts. So this is why the story needs to be gone, and to really match with the LIGO observations, you need to go to pretty high post-Newtonian order to get a full inspiral. And then you need also to use this data from numerical relativity to match this part. Otherwise, you reach too quickly the ISCO, the most stable circular orbit in this area here. So that's what I wanted to say. Do you have questions about this?
Maybe I have a question.
Yes.
What is the meaning of this ISCO exactly? I didn't quite get it.
So the ISCO is the last stable circular orbit. So it means that beyond that orbit, circular orbits are not stable. So it means that if you perturb them a little bit because of gravitational reaction, for example, then it will plunge into the black hole. It will plunge.
Okay, thank you.
So if you have this concept is really for a geodesic around in the background of a black hole, so if you orbit very far away from a black hole, you can orbit with circular orbits. But if you are too close, you just fall into the black hole. It's just any perturbation, you just fall into the black hole. So you expect that for the binary system, there is an analog that if they are too close to each other, they will just plunge into each other, and they will not evolve through quasi-circular orbits.
Okay, thank you.
This is this breakdown of this post-Newtonian formalism, because you start from a quasi-circular or Keplerian motion.
Sorry, can I ask a question?
Sure.
Yeah, so this F max that you obtain here involves 1 over m. So if m is total mass is less, then the maximum allowed frequency increases, right?
Yes.
So can we see the other constraint?
Which constraint?
The one from.
Yeah, I'm not sure which other constraint you want.
Yes, the one in which V over C.
The frequency.
Yes.
I mean to compare with the quasi-circular inspiral.
Yes.
I should have compared the two. So I think I wrote it down somewhere. It was before, I think.
Yes, here. Yeah.
This one, yes. Yeah, I should have compared this one. So actually, this one occurs afterwards. So the ISCO is first. If you compare the two, so what breaks down first is the fact that you are closer to ISCO.
Okay.
That one breaks down later. So actually, this one is not that relevant at the end.
Right. But still, before that, I mean, this analysis is useful to. I mean, in the earliest stage of the spiral, right?
Yeah, of course. It's just that for this particular event, you don't see the earlier inspiral. You see too late. You see it too late. So you cannot match the entire inspiral. So this inspiral it will be seen very, very well with LISA.
I see.
For the extreme mass ratio binaries, the one with the very large mass ratio, most of the time in the LISA band is for the inspiral phase.
I see. Okay, thank you.
Yep. Are there more questions? So if not, so I see you tomorrow, and we'll talk about black hole perturbation theory that time. So see you there.
Thank you.
Thank you. Bye-bye.
Thank you. Bye.
Thank you.
Thank you.
Thank you.
Goodbye.
Thank you.
Bye-bye.
Thank